Okay, everybody. Welcome to this week's talk. We have Francisco Manuel Castela Simão.
Simão, yeah,
Simão. Coming to us from Queen Mary University of London. And this is the part 2 of the Battle Royale for Quantum Jet Bundles. So the title is Quantum Jet Bundles.
Hello. Well, first of all, thank you very much for the invitation to come here give talk on quantum jet bundles. And from what I understood, at the end we'll have a fight between me and the 3 other people working on the subject. So all of this research, so this is research that I was doing during my first year of my PhD with my supervisor, Shan Majid. You can, so if you like the talk and you're interested in reading further, you can just go to the archive. And so you can find the paper at 2202.03.067. Yeah. Okay, so the long-term goal of our project, or so the idea that we had to, or the reason why we wanted to look at quantum jet bundles was, so the motivation comes from physics, and it's because, so these kind of structures, I'll talk about them a bit later, they allow us to, so our hope is that they allow us to define some sort of non-commutative field theory via, via a sort of non-commutative variational bicomplex. So what is this variational bicomplex? And so the idea here is that if you're doing classical field theory, the way to formalize it mathematically to look as this complex. And the thing is, so we have a bicomplex, is bigraded. So we have 2 differentials, and these 2 differentials give you exactly, so the, sorry, +1. So these give you exactly the differentials that you're interested in physics. So the first one, the horizontal one along the base, so this will be, so you get this complex from the RAM complex of the infinite jet bundle. And this, for now, just think of it as some sort of bundle over a base manifold M, which would be our spacetime. And now this, so we can build this jet bundle, and if we build the 2 differentials of this complex, so we can divide it into horizontal differential and vertical differential. So this would be D for, so the horizontal, and this the vertical. And the interesting bit about this is that, so D just gives you some sort of analogous differential to the spacetime differential. So what that we all know and love, I hope. And this here, so this is the interesting bit. So usually in physics, what we want to do is calculus of variation. So you have a curve, you perturb this curve a little bit, and you try to minimize some function on the curve. And in non-commutative geometry, so we cannot simply do this because we don't have curves in spaces. But through this formulation, so this lets us formulate these variational derivatives in a cohomological sense. So here the idea is that we have a base algebra, we do some, we build some differential calculus on it and so on. And then we can find the differential that just encodes the variational derivatives. And if we have this, then we could get all kinds of interesting stuff that we want in physics. So we could have so if we have an action, we could derive the Euler-Lagrange of motion, the Euler-Lagrange equation of motion from it. So Yale equations. If we have this, so Noether's theorem also has a very nice, neat way of being described in this. Yeah, so in this setting, so we'd have Noether identities. So Noether identities and conserved currents and so on. Etc. And yeah, but before we can look at this, we first need to understand this object here. And this is so a first step into getting this big picture. And we'll see how, so in our formulation of the jet bundles, we'll get to consider connections. so bimodule connections in non-primitive geometry. This will lead us to some braidings, and we'll see also a bit of well, I won't talk about it too much, but in our formulation, so Hopf algebras also, so braided Hopf algebras also play a role through this braiding coming from the connection. Okay, so that is the motivation. Let us just review what the jet bundles are so that everyone is comfortable with what's happening. So classically speaking, jet bundles are just, so if we have any fiber bundle over a manifold M, so we have any fiber bundle over M, then we can build the Cave jet bundle over from this bundle. So this would be just written like this. And the idea here is that, so the fibers of this bundle, if we have so a fiber of JKE at the point X, where X comes from the manifold, this is just so a set of equivalence classes, which we denote as such, where S is element of, so this curly E, I'll just be using for so the space of sections of the vector bundle itself. Yeah. Sorry, the fiber bundle for now. We will be looking at vector bundles in general later, so only vector bundles. But yeah, so now it's fiber. Thank you very much. Yeah, and so these equivalence classes, you can think of it as a set of all sections that have the same Taylor expansion as a section S up to order K at a specific point. Right, so if two sections have the same Taylor expansion up to order K at the point, then they belong to the same class. Okay, a map here that is of certain, so that's quite important in this setting. It's what's called the jet prolongation. And this is a map, so JK E, that goes from the sections of the fiber bundle to the sections of the jet bundle, which I'll also write with a curly J. So I'll write it like this. So just sections of the jet bundle. Yeah. And the idea here is that it takes the section S here to so J of S, so JK of S, which would just be the Taylor expansion of S. So we'd have locally we'd have S, then the first partial derivative of S, then the second, and so on and so forth, until we reach the Cave derivative. Right? Are there any questions about this? So if you have questions, I don't know how I usually do it, but just feel free to interrupt. Right, and as you might have guessed, so I've also made this mistake while talking earlier. So here, what we want to do is we want to look at vector bundles, because when this original bundle is a vector bundle, then this jet bundle is also a bundle, right? And we can use the Series-1 theorem, so to pass this to non-commutative geometry, because so vector bundles over the base manifold are modules over the, so yeah, so vector bundles are just C infinity M modules, so modules over C infinity M. And so since when the original one is vector bundle, so the jet bundle is also a vector bundle, then the question that we want to answer basically is, so we have several questions that we want to look at. Is that, so if we look at the, so generic algebra A, so if we have just a module over A, so in our setting, we look usually at bimodules. So if we have bimodule over A, how can we build from this a bimodule that would correspond to the sections of the jet bundle over A? So sorry. Yeah. So yeah. So the question is also, what is the exact module structure that we have here? And we'll see how, so what inspired us to build our specific module structure that we have. And what is this jet prolongation map? So in non-commutative geometry, we'll go over it, but so a first order differential calculus gives us a first order derivative, but then the question is, how do we build higher order derivatives in here? So what is J? So J, yeah, J key. And to answer this, let me write it here. We have two sequences coming from classical geometry that guide the way, so to speak. Okay, so the first one is called the T exact sequence. Of C infinity M modules. And this is a sequence that entails information about the first order jet, so first order derivatives. And the sequence goes like this. So 0 goes to omega 1, the space of one forms tensor. So tensor over infinity M of E. Goes to the first jet bundle. Goes to E itself, so the module itself, or space of sections, goes to 0. And this exact sequence is split. So we have a map here. This map is exactly the jet prolongation map that I was talking about before. So this one for k equals 1. And we can show that splittings. So an interesting fact of this is that splittings of this form J1E correspond exactly to connections on the vector bundle. Right, and so the important information that this sequence gives us is that for this to be a sequence of modules, so in this first module and the last one, you have the module structure that you'd expect. So if you multiply it with a function on M, you just have pointwise multiplication. But in this module here, so is there a question? No? Okay, sorry. So in the module, so this is split so that you know that as a vector space, we can write just J1E as a sum of the two others. So if we write this like this, so omega 1 tensor infinity of M, tensor E, then applying a function f, or multiplying from the left, so f is in sin infinity of M, with an element of this space, which I'll just write it as S plus omega tensor T. So we get two terms that is exactly what we expect. So we just get normal multiplication for once. Sin infinity of M T. But then we get an extra term, which includes the first derivative of f. So we get the term which is the f tensor C infinity of M S. So we see that somehow in the model structure, the first prolongation of f plays a role, right? So the first prolongation would be f and its first derivative, which is encoded through the differential. So we see that the module structure of this thing here is not so trivial. And the second one, well, let me write it here, just not to go to another board. The second exact sequence that kind of led the way for us to see what the structure of this jet space should be is this one. So the jet sequence. So you go from 0 to omega ks. So omega ks here are just the 0k symmetric tensors. So just tensor product of omega 1 k times, and then we symmetrize everything. This goes tensor C infinity of M and then E. This is included then in JKE, and then this can be projected down to JK minus 1 E goes to 0. So this is just an inclusion. When you go from JKE to JK minus 1 E, what you're doing here basically, if you look at this bundle, what you're basically doing is just erasing the last bit of the Taylor expansion, right? So you have a Taylor expansions up to order K, and then the projection down is just erasing the last term so that you have Taylor expansions up to order K minus 1. Okay, so the idea then is that if we have an algebra A, so our idea was giving algebra A, we can build the first order differential calculus. I'll give definition a bit. So this would be just the analogous of one forms over on the base manifold, but the non-commutative version. So given this, we can then, yeah, of course. Thank you. This is fine. Yeah. So then from this, we can build the symmetric part of the K tensor product of omega-1 to the tensor product of K. And we'll see how we build this symmetric part. So I'll define it later. And from this, we'll then somehow build the vector space structure of this module. And then from what we'll do, and so our idea was to use connections to define these jet spaces. So this jet prolongation maps, sorry. For the higher order derivatives, this will be clear in a second. So here we have connections, or rather bimodal connections. So yeah, which will give us then, as we'll see, some sort of braiding. So let me just write sigma for now, and this will then help us define the exact module structure that we are looking at. So this is just a general idea of what will be happening. Okay. Any questions so far? Can I write here, or the people in Zoom? Because okay, it's fine. Okay, so let's define this and see what we're talking about. So given an algebra A, so probably most people are familiar with this, but a first order differential calculus on A. So given sorry, first order differential calculus on A is, so what we have here is just A being an algebra. So A is an algebra, algebra A. Then we want a module over A. So this would be just, we write it as omega-1. This is an element of the modules, of the bimodules over A, which you can think of as a space of non-commutative one forms. And this, we wanted to have the forms omega-1 is equal to A dA. So by this, I just mean all elements of the form A dB, where A and B are in A. And then, so this D, I haven't defined it yet, it's just a differential, which would be a map that goes from A to omega-1, which satisfies the Leibniz rule, such that, so D AB is equal to DAB plus A dB. So this is just the bare minimum of what we can extract from one forms in a classical geometry. And then, so if you want, you can also extend this to a differential grade algebra, which would be the differential grade algebra of forms over an algebra, non-commutative algebra A. Here, what you do is you just take omega to be the tensor algebra of omega-1 quotient by some ideal. And this ideal will give you the relations. Then we impose as well that d squared is equal to 0, and the product in this algebra would be the wedge product that just goes from omega n. So this would, sorry, let me just write that this would be the direct sum over n of some omega n. So the n forms, again, d squared is equal to 0. And then the wedge product would go from omega n, omega m, goes to the sum of two. So omega n plus m over A. Exactly. And so, and this ideal just basically gives you the relations of the wedge product. Classically, this would just be the antisymmetric relations. In non-commutative geometry, we can pick technically whatever we want. Okay, and with this, we can already build our first order differential, our first order jets over A. Sorry, I was a bit too aggressive there. So J1A, we've already seen this. So we've seen this for, for a generic vector bundle, but now we want to, sorry, I forgot to mention one thing. This, so what we want to do is, this works for any vector bundle, so for any module. What we'll start by doing is to see how it works when the module itself is the algebra. So E is equal to A, because this is the simplest case that you can have. And then from this, you can generalize it, not straightforwardly, but it's then easier to see what the whole picture looks like. So first, looking at the jets of, in the case that the module itself is equal to A, what we do is just, so we set our space, our module of first order jets as just being A plus omega 1, so the direct sum. We have that our prolongation map, so J1A going from A to curly J1A, is just, so we define this as just being, so if we take an element in a S, so S for section, this is just S plus ds. And the bimodule structure here would be structure. So this would be analogous to the one that we have found here. So in this case, we write the action of the algebra on the module as a bullet. So just bullet 1. And so bullet 1 on S plus omega. So S plus omega is in this space here. This would be, so J1 A times S plus A omega. Can you see this other computer here? Yeah. So, and if you write this out, so you get exactly what is here. So J1A times S gives you these two elements. And then the last one is just this one. Right. Yeah. So the other thing is that here we are considering this module as being A itself. So these terms, these extra terms here with a tensor product, we just have theta product over A, and that just vanishes. All right. Any questions so far? Since I have to clean the board. Okay, if not, now the question is, we have our first order derivative, and we know how to define it. The question is, how do we define the second order derivative? And our idea to do this was via connections. And you see in a bit why, but the idea is that, so if you have an algebra A, D takes us to omega 1. And now we want a map that takes us to omega 1 tensor A omega 1. And the map that does this is exactly what we call a connection. So a bimodule connection, bimodule connection on so on an A module, so on an A bimodule. This would be just a map, so that we write as nabla E, going from the module itself to omega 1 tensor AE. So the usual notion of a connection, if we take E to be just a section of a vector bundle. And then we have a braiding map which so braids the module itself with a space of 1 forms. And the reason why we need this is that we want the connection to satisfy some sort of Leibniz rule. So if we have now A in A and S in E, what we want is that, so now we'll apply to AS. This gives you the usual, so classical Leibniz rule. So this is just the differential applied on A tensor S, and then A, then nabla applied on S. And but from the other side, so if we multiply a section S with an element A from the other side, what we have, so this term, we have an analogous term. So S and then A. We multiply nabla ES with A. And then what we'd have from this intuitively would just be S tensor A dA. But this lands in E tensor omega 1, which is not the space that we wanted to land in. So that's why we need a braiding. Yeah. No, it's fine. Yeah. Yeah, so this is why we need the braiding. And so important to say is that whenever we have a connection, if this braiding is defined, then it's unique. So that there's no ambiguity there. Yeah, so if we have a connection, if this exists for a specific connection, then it's unique. It does not always need to exist, but if it exists, then there's no ambiguity in the choice of braiding. Yeah, so
classically,
just a flip.
it's
Just a flip. Yeah. Okay, now I just want to go quickly over some properties of connection. So one that we'll need is that we can define the notion of curvature. So the curvature of a connection is just so we can build it as a map that goes from the module to omega 2. So for this notion, we need two forms, tensor A, E. And so just to write it down very quickly, this is defined as such. So definition is not very important for today, but this recovers exactly the classical notion of curvature. And we say that a connection is flat. So nabla is flat if this map is 0, as you'd expect. Now, given that, and then so if we take, so E to be just omega 1, then we can also define the torsion, which we define as a map. So now, right, so nabla omega 1, going from omega 1 to omega 2. And this is defined as T nabla omega 1, which is just equal to wedge nabla omega 1 minus D. So the way to think about this, so this just recovers a classical torsion. The way to think about this is that it's the difference between the two ways of going from omega 1 to omega 2, right? So we can use D in one side, and the other side is taking this to go to omega 1 tensor omega 1, and then using the wedge to go to omega 2. So yeah, so torsion free is then as you'd expect when this map vanishes. And this map is not always a bimodule, but so one condition that will be important for us is that if this is a bimodule, so bimodule map, then we have, so this is equivalent, or this implies a condition on the braiding, which is just this. So that's so the image of the identity plus the braiding itself coming from the connection is in the kernel of the wedge. The way to think about this, if you're familiar with braid diagrams, it would look like this. Is equal to 0. So where this is the wedge, here we have omega 1, omega 1, omega 1, going to omega 2. And here is the braiding. And the way to think about this is, so classically, this would just be the flip map. So what we have here is a symmetrization operator. So we take tensor product of two forms, we take the identity and then the flip of the two. And it just says that this thing is in the kernel of the wedge, which you'd expect. And it's just a generalization to any kind of braiding.
This is going, if it's going off the connection.
Sorry?
You wouldn't the implication in one direction.
I'm not sure. That's why I don't remember. Yeah, I think it does. I think it does, but I'm not sure. So you can check Sean's book and it's yeah. And so when a braiding satisfies this condition, we say that the braiding itself is torsion compatible. I have to start writing small. Yeah, so any questions so far?
If you have the torsion compatible, is it?
No, this is a torsion compatibility.
Right. And if you have torsion compatibility, is it?
Yeah, so I don't remember. I think so. But I don't remember. Okay, then does it? Because this, you're not saying that you are describing the whole kernel through this equation. It's just a subspace of the kernel. A subset, yeah. Yeah. Okay, so now we've seen we are ready to build J2A. And yeah, so for here, the ingredients would be just like a first order calculus connection, as I've mentioned this time. So connection on just omega 1. And another thing that we need is, as I mentioned before, so I just erased it, but that we saw in the beginning that symmetric forms play a role in this whole construction. And for us, we defined the space of quantum symmetric 0-2 forms. So the space of quantum symmetric we call it two forms, but they're technically 0-2 tensors. This would just be, so we write this as omega 2s. It's just the kernel of the wedge, which is in omega 1 tensor A, omega 1. Okay, and now, as I've said here, so the idea is if we are given a connection, a connection that goes from omega 1 to omega 1 tensor omega 1, we can define the second jet space as so we take as a vector space, you just take J2A to be so A plus omega 1 plus omega 2s, so this symmetric forms, and we take the jet prolongation map, so small j to A, as being the map that goes from A to j to A, sorry. And it just takes an element of A, and it gives two terms that we already had before, so first order derivative and second order derivative. And it adds, yeah, so it adds this extra term that we want, so that we interpret as giving us the second order derivatives. then its module structure.
Sorry, I should probably say there's a comment from Edwin in
Yeah.
the chat, and he says, yes, the implication does go in the other
Thanks,
direction.
Edwin. Yeah. Yeah, so and the module structure of this space is that if we multiply A with a generic element on this, so this I would write as S plus omega-1 plus omega-2. So here S is from A, omega-1 from omega-1, and omega-2 from omega-2S. This will be something similar to what we saw before. So what we do is we multiply the second jet of A with S. Then we have a term that involves the first jet, but it's a bit more complicated. So A omega-1 plus, then we have this graded integer that I'll define in a bit of the A tensor A omega-1 plus A omega-2. Yeah, where, so this thing here, if you're not familiar with it, is just the symmetrization that we saw before. It's just this identity plus sigma. Yeah. And what we've shown, so this is the left module structure, the right module structure is completely analogous to this. Yeah, of course. Nothing, I was just singling out this element, sorry, we don't need this. Because as you can see, so in the curly bracket, so what you have is that in the zero order elements, you're using the second jet of A. In the first degree, in the degree 1 elements, you're using basically the first J of A, and then you're using the 0th J of A in the last elements. So I just want to stress out that point. Thanks for the question. So right module structure is just very similar to this. And the theorem that so what we proved here, I'll just write it here very quickly, is that so the connection that we have chosen here is torsion free. Is torsion free. So in particular, torsion free means that, so torsion is 0, so it is automatically a bimodule, so we have this automatically. Then this will be a bit cramped, but then we have that J2A is indeed a bimodule, and that this J2, so the jet prolongation map is a bimodule map. Is a bimodule. No. So the reason you need this is to ensure that this whole expression is indeed in the symmetric part here, and also for this bit, you want to ensure that this is symmetric. And so if the connection is torsion free, what you see is that applying nabla here. So torsion is 0, so this is just D. We have D squared, and that vanishes. Right? Yeah. So the property that this is torsion free is just to ensure that this map lands indeed in the right space, and that the module structure is also consistent. All right. So now the question is, we've seen what we need to build J1A and J2A. Are there any questions so far? Yeah.
Right. So you said the sigma is uniquely associated to the connection. But then, so how restrictive is being torsion free then?
You need to take torsion free connections. That's the.
Okay.
So you can just choose a connection, and you can see, okay, is this connection torsion free or not? And some connections will be, some connections won't. Yeah.
But I guess my very naive question is, how difficult is it to find a torsion free?
Not difficult at all. So
okay.
Torsion free is fine. Exactly. So if you classically have Levi-Civita connections, which are always torsion free, you just like that. Okay, so but now the question is we have this torsion free condition for J2. The question now that turns out to be much more complicated is what happens for higher order degrees. And what we found is that so for the degree k equals to 3, you need to impose a couple more conditions. Yeah, so you need to impose a couple more conditions, but after J3, you don't need to impose any more conditions on the connection. So we'll see that we need, I know, 3 more conditions on this. But from J3, we don't need anything else.
Can I also ask, I guess, so when in the commutative case, this all reduces down to the second jet bundle.
Yeah, so in the commutative case, so if you choose a specific connection, then this reduces to the jet bundle. I'm not entirely sure on one specific thing, so if you, and maybe the other 3 like researchers that are looking at this can answer, is that so if you have the jet bundle, it's just a vector bundle, and if you, so classically just as a vector bundle, you build the sections of it, and the module structure of the sections, I think, should be just pointwise multiplication.
There is a bimodule structure, actually, and not for me to do a bimodule even in the classical setting. You have the action that you're talking about, which is just the pairwise multiplication method function. But also you can multiply functions onto the function that you want to take the jet of before, and then you lift this up and you extend this to an action as well, which we interpret in our construction as the right action.
Yeah.
And in this sense, it does not split as a bimodule.
Yeah, and I think this action that you're talking about is actually this more complicated action that you have here.
Yes.
Yeah. So this is something I noticed yesterday while talking to them, that if you take this with the 2 different actions, so just pointwise multiplication on one side and this more complicated one, then it would reduce to the classical jet bundle. Yeah. Then there is also, so another caveat is that our choice of connection here is not unique. So given an algebra and one forms on an algebra, you can choose a lot of different torsion-free connections, right? I can tell you which one gives you the classical, so the classical construction for a couple. So if you have classically, I can tell you which connection gives you what you'd expect. But in our construction, you could choose any other torsion-free connections.
And then, of course, the bundle will depend upon this choice of connection.
The bundle itself, yes, because it appears here.
Yeah.
So as long as classically, so because on the other terms, it really only depends on the braiding. But on this part, and
But I guess then the braiding is coming from the connection.
Yeah, but different connections can have the same braiding. So different connections can give the flip. Yeah, for example.
Okay, so that the first term depends upon it, and then the second term depends upon it up to some equivalence relation.
Yeah.
Okay.
I think so, yeah. Thanks. Okay, well, this took much longer than expected. Sorry for that. The seminar is usually 1 hour. Okay. So we'll just go quickly over on how to build the higher order jet bundles. Okay, so now the question is how to build higher order derivatives. And it would be, so if we take the sequence now, what we want in our so in our way to view things would be to build a connection on this space, omega1, tensor omega1. But thankfully, so what we can do is, so we can build what is called a tensor product connection. And what this construction does is basically if we have, so 2 modules, so E and F being A modules, so with connections on them, so connections with braidings, so nabla E sigma E and nabla F sigma F. Then we can construct a connection on the tensor product by module. So then we have a connection. So we have a tensor product connection on E tensor F with also braiding on E tensor A. Just to be quicker, I will yeah, so on the tensor product. Just to be quicker, I'll just skim over the details. Also, the specific form of this connection is not important, just important that we can do it. Yeah, so then having this, we can define the nth order derivatives on an algebra, dependent on the connection that is chosen. So the nth order derivative on A. So our idea is just to take, so we call this so nabla n going from A to omega 1 tensor A n. Right, and what we do is just, so we take an element and we apply these connections over and over again till we get it. So, right, so we apply, we get dA, which just takes us to omega 1. Then we apply the connection on omega 1 at the second order, and then we go to, so omega 1 tensor omega 1 A until we reach the last one, which is just the connection. So from the tensor product connection on omega 1 to the n-1 tensor power. Derivatives. Is there a question? Sorry? Yeah. So this would be what I've written here. This bit. So this is just what's happening here in the end is, so A is going to omega 1 through D. Then you go use the connection to go to omega 1 tensor omega 1. And then, well, if I can get it like this, use the connection on this thing. So because, so we have a connection omega 1, connection omega 1, build a tensor product connection on this space, and you use this, which I call so nabla omega 1 tensor omega 1, going to omega 1 tensor omega 1 tensor omega 1. Then you do this repeatedly. It's not. It's not. Yeah. So that leads me to my next point. So we need extra conditions on the braiding, and just to skim over it. So if we have a braiding, so sigma E, that goes E tensor omega 1 to omega 1 tensor E. So this is called extendable. So extendable and wedge compatible. If we can basically extend it to two maps in a consistent way that braid E with omega 2. Okay, so if we have two maps, E omega 2 going from, so swapping these two. So E and omega 2 and from the other way as well. So E going to EA. Yeah, and the way that we do this is yeah, so basically, so we can imagine that we have this is defined on two forms, and two form you can get by the wedge product of two one forms. And what we want in the end is that, so the braid diagram for this thing would look something like this. So we start with E omega 1 omega 1. here we have the wedge, and then this would be the braiding that we just constructed. Sigma E omega 2. This would take us to omega 2 sigma, and the way we define this is that we can basically define this in terms of one form. So what I mean is we'd get this diagram instead. Omega 2 E, and here you have the usual braiding. Right, so the way that you're defining it, you just, so instead of writing the wedge product, just braid everything before, and then you apply the wedge product. This makes sense. And for the other one, you'd do exactly the same. And yeah. Okay, then what we need as well is that, so notion, so if we have a braiding omega 1 tensor A. So braiding just braids omega 1. We say that this obeys the braid relations. Braid relations if, so I imagine that most people are familiar with this. If we have a diagram like this, never know how to write it. Yeah, so if we have this diagram omega 1 going everywhere, and could we extend the talk by a little bit, or because it's 5:02?
Yeah, no, I mean,
It's fine. It's okay. Sorry for that. Yeah. Okay. So what we want to do now is, if we have these conditions, we want to build an algebra structure on. So we want to build the space of quantum symmetric forms, and it turns out that the module structure of the K-jet bundle, or of the N-jet bundle, can be quite easily described as as if we take into account the algebra structure of the symmetric forms that comes from this braiding, and I'll define this in a bit, which for the people that are familiar with it can be used or can be defined by the braided binomials. Yeah, binomials. Sorry, yeah. Okay, so just so the space of quantum symmetric K-forms K-forms omega Ks. So we just take this as so simple definition as the joint kernel of the wedges. So this would be in omega 1 to the K tensor power with respect to A. And by this I just mean, so an element in here is just an element that if I apply the wedge to any space gives 0. So this I just means by applying it in the different spaces. And then, so this braided binomials, the idea here is that given, so braiding that goes from omega 1 tensor omega 1 to itself, then we can define the braid binomial maps. So the braided binomial maps maps are, so we write this as n over k with respect to the sigma, and we can define them in various recursive ways. So, but the idea here is that given this map sigma that basically swaps omega 1 with omega 1, we can build these maps that go from omega 1 n to itself. And the way to think of this is that these maps just give us some sort of shuffling of these tensor powers of omega 1, right? In very different forms. So I could write the definition, but I don't think that that would give you any intuition for what's happening. The way to think of this is just different ways of shuffling what's happening in here using the braiding. Okay. So now what we have is that so a small proposition is that if this braiding that we have is various things, so if this is torsion compatible, so this was just to recall that wedge identity plus sigma is equal to 0. If it is extendable and so wedge compatible and obeys the braid relations, then we have an algebra. So then we can build an algebra which is just so omega s as the direct sum from n equals 0. So where the 0th degree is just the algebra itself until infinity of omega k and s. And this product that I just write as a circle with a dot. And this product here is just defined as, so if we look at individual degrees, so going from omega 1 to the if tensor power, tensor a omega 1 to the jth tensor power, and this goes to the sum of the two, so omega 1 to the I plus jth tensor power. And this is just, so we just take these braid binomials that I was talking about. So if you take these specific braid binomials, then we can, sorry. So what you can think of it doing is you take, so form that is in here. So just with I, one form censored with each other. Then you have J, so J form censored with each other. And what you're doing here is just shuffling them in a specific way to get something in here. And what we proved is that if you start, so that this reduces, what we proved, no, sorry. So Shan and Tao proved this in 2015, that this reduces to, yeah, so just omega I s tensor A, omega J s going to omega I plus J s. So you'd have a product like this. And now, last but not least, we need one more condition for the jet construction to work. Let's use this. And this condition, are any questions about this? By the way, forgot to ask. So, so the last condition here is that, well, let me write this as a lemma. So if the connection that we have is Leibniz compatible, if this connection is Leibniz compatible, which we, so this is a condition that we had to come up with, compatible, by which I just mean that we can swap the connection and the braiding in a specific way. So this would be this equation. Identity. So applying the braiding and then the connection on one form tensor one form is the same as applying the connection first and then the braiding on the second bit. So this is a condition that we have. Then the nth order derivatives that we described, that we defined before as just this composition of the various connections, satisfy some sort of nth order Leibniz rule. So the way that this looks like is that if we take the nth derivative of A times B, for A be in the algebra itself. This can then be decomposed as a sum from k equals 0 to n of the n minus kth order derivative of A. And then this product for the symmetric algebra, so times this nabla kb. What's happening here is, so this is just a sum. So we can write this with the braid binomials, and you might recognize this as exactly the formula that you get classically. So if you apply the kth order derivative or the nth order derivative to a product, then what you get is a lot of summands with the binomials. So instead of having the braid binomials here, you just have the usual binomials. The what? Ooh, which one is that? Yeah, maybe it is, but yeah. Okay, and so one thing, so this condition felt a bit strange, but one of the reasons why we didn't feel so bad about imposing it is that this condition also implies a braid relation. So if this is true, then sigma obeys the braid relations. So sigma obeys the braid relations. So Leibniz compatibility implies braid relations. Okay.
Is this difficult to see?
Sorry?
Is this difficult? I mean, the proof that it implies the braid relations.
I don't think so. You just need to write this in. So if you write this in braid diagrams with definition for this thing, you just apply the wedge in specific places, and I think you get this back. You can check it in the paper. Yeah. Okay, and we can finally come to the main structure that we defined, which is a Cave jet bundle. And so, having all of this in mind, so if we have a connection on omega 1, so omega 1, sigma omega 1, which is fulfills all of the conditions that I talked about before. So this would be torsion free, flat. So we also need it to be flat, which is something that didn't come up until now. For it to be Leibniz compatible here, for it to be extendable and wedge compatible. So the two things that we have here. So if fulfills all of the above, I never know where the double L is. All of the above, then I think here. No, the other one.
You're right.
Sorry?
You're right.
It's on this one? Okay. I'll just leave it double L on both. Then it looks extremely bad. Okay, so now what we can do, so we define the jet bundle as, or the bimodule itself. So here we can just take the sum for j smaller than k, so the kth or jet bundle of omega js. And we can take the jet prolongation map, so jk, going from A to the kth order jet bundle. This is just then, so jk A. This will then just be the sum of all derivatives upward to order k. So I is equal to 0 up to k of nabla IA, where of course here, so the 0th order derivative, I just mean A itself. So this with the module structure given by, and so the module structure now actually simplifies quite a bit. So if we have an element of the algebra A, if we multiply an element of the algebra with omega j, where omega j for me is just in one of these spaces, of the symmetric spaces, then we define this as just the kth minus j jet of A, and then we take this symmetrized product with the binomials times omega j. And this is the module structure that we have. And same for the other side. So omega j equals k A, similar. So exactly the same, but from the other side. Omega j, and then symmetric product, and j k minus j A. So then this is a module. And yeah, and the jet prolongation JK is a bimodule map. Okay. Just one comment is that so if we have the kth jet bundle, we can always project it down to JK minus 1. So we have this sequence that goes down, and having this, we can also define the infinite jet bundle as the inverse limit of the sequence, which then, so it was the whole motivation for the thing that we can then use to build the variational bicomplex, which we haven't done yet. But yeah, I just wanted to mention that. And yeah, given that we're already 10 minutes over time, I think I'd stop here. Sorry for not showing any examples or what I wanted to show them, but yeah. Yeah, so thank you very much. Are there any
questions? Maybe we should pass it to the There's the mic just behind you.
Can you hear me online now? Seeing if something appears. Okay, so first, I don't know if you're familiar with it. There's something called the Arnold principle.
No.
Which says that nothing in math is ever named after its discoverer. And in that vein, I would like to say, I think the Atiyah exact sequence is due to Quillen.
Okay.
If Andre were here, he'd also make the comment that the Arnold principle obeys the Arnold principle.
Sorry for comparing to what happened last week when you weren't here, but I want to say that our starting points, starting ideas were pretty different. You are interested in physics, in the variational bicomplex. We were interested mainly in representing differential operators and properties of those. Then we converge because we both went towards the Atiyah or Quillen exact sequence, whatever you want to call it, and we tried to do something with that. And from that point, we diverge quite heavily.
Yeah, I agree.
And the interesting part for me about that is that the assumptions that we need to make are completely different. In particular, if we want to go above jet order 3. I would like to also make the comment that I think it's really strange that these two different approaches to non-commutative jets both become much more difficult above order 2 specifically, because third order jets was a difficulty for us as well.
Yeah, for us, we spent a lot of months on it.
Yes, exactly. Yeah. So it's kind of strange that seems to be the universal order where things start to get difficult. Maybe there's some reason for that. But in any case, we need to introduce at this point a lot of homological assumptions on the modules that are involved. We're always saying, well, let omega 1 be right flat, let omega 2 be right flat, blah, blah, everything is flat, some cohomologies need to vanish and so on. Lots of homological assumptions. But you seem to put all your assumptions in a completely different place, which is in these connections and gradings that you have. So I was wondering, does the existence of these connections with these special properties imply anything homologically about the bundles that you're able to treat, or does the existence of connections just give you some homological information? Like, do you know that the bundles are well behaved if they admit such connections?
I can answer the first one if you want. Quillen, again, tells us that it's projective with respect to the universal calculus if and only if it admits, it's projective as a module if and only if it admits a connection with respect to the universal. So the existence of connections is closely connected to projectivity. For a general calculus, I don't know.
I also don't know. I know about the result for universal, but this is not for universal, right? So
This could be anything.
it's curious to me that you have no homological assumptions to get these results.
I think it comes from the fact that the connection is flat. Because when the connection is flat, then you can build a complex from that. And so, yeah, we were asking ourselves also what would be the bridge between our assumptions and your assumptions. And maybe it comes from that, but I don't know. So because if the connection is flat, so I just want to mention that maybe it comes from that. So if this is flat, or let me write it like this. Wait, sorry. So if we can build a complex that goes from a module E to just omega-1 tensor E using the connection. And if this is flat, we can show that, I think, if you take then the connection on omega-1 tensor E, so the tensor product connection that I talked about before, and you continue like this, then you get a complex where this squared equals to 0. It's basically equivalent to flatness. So I don't know if we could use this somehow to go back to your assumptions. Sorry? Yeah. So maybe this is one way to go, but I'm not sure.
So second comment, which is more of a suggestion, something you could do if you want. What you have constructed here is what's called holonomic jets, which is basically synonymous with jets in general parlance. But there's also other kinds of jets like non-holonomic, semi-holonomic, sesquiholonomic. And I think you could investigate also what the semi-holonomic jets for this construction would be, and whether the holonomic jets then embed into the semi-holonomic ones. It would be interesting to know.
Can you briefly describe what these are?
Yeah, so non-holonomic means that you take your module, you want the second non-holonomic jet, you take the jet module, and you treat that as a vector bundle on its own, and take the first jet module of that. So you take J1 on J1.
Yeah.
And take J1 K times, you get the K. Non-holonomic jet. And on these modules, you have a lot of different projections down to the n-1th non-holonomic module. If you take their equalizer, so the case where the submodule where all projections coincide, you get the semi-holonomic jet module. And you can show that the classical holonomic jet modules are also semi-holonomic, so they have only one jet projection.
Yeah.
Which is the one that shows up in the ATIA or Gulen, if you want, exact sequence. So they should have this semi-holonomic property as well. And it would be interesting to see if everything.
Well, what it is here. Case. Yeah, sure. Thanks. Any further questions?
I'm going to ask you quickly to about examples then. So, I mean, the first question would be like Manuel spoke about last week. I mean, well, first of all, maybe before that, you can define a differential operator, then I guess is something that factorizes through the jet bundle.
Yes.
Yeah. And then will things like exterior derivatives and connections be differential operators?
I'm not sure.
Okay,
but I'm guessing, yeah, and I think that Arjen was working on this, and he showed some equivalence between differential operators and the existence of a connection that you can use. Yeah, so you can use connections to define differential operators.
And then, so for, let's say, for concrete examples, then where this is worked out, I mean, for Padlish, does it work?
I haven't tried so the thing there, I tried so CQ SU2, and I restricted myself to left invariant connections. And there, so I want to review the calculations. I was just doing them last week, but there I don't think it works, and it broke down in this Leibniz compatibility thing.
And this switched for the 3D calculus of the bicovariant before
3D.
3D. Okay.
Yeah. So I guess so the next step, we looked at left invariant connections so that we don't have to look at the whole moduli space of connections. And yeah, so the next step would be to look just at any connection on CQ SU2. which might be a bit complicated. Yeah.
Podlish is going to be better because everything works better on the
Mhm.
flags. So
Yeah, I have to look into that. So the examples, just to go over them quickly, would be, so just if you have a omega 1 with a central basis, this works, and you just take so for a central basis, if omega 1 is just the span of some EIs, then you can just take the connection which vanishes on these EIs, and then this works, and this basically recovers the classical case. Then, so the other examples that we had it on the CS3 on the functions on the group S3, and there it's quite interesting because it gives you a more non-trivial connection, because here, so the braiding is just a flip, but if you go to the algebra functions on S3, you get the braiding which is non-involutive, so it gives us strictly braided thing. So 2x2 matrices as well, but they just also have minus the flip, so it's quite straightforward. And in the bicross product for Minkowski in 1+1D, there we actually found two connections. One is involutive, the other not. So that is so that begs the question, so are these two connections somewhat equivalent? Because so both classically and in their so in their formalism, you have a unique construction, and for us, you can just pick any connection and do what you want. So that is also an open question: is in which sense would these two constructions, by picking two different connections, be comparable or not? Yeah.
questions or any from online?
If they are still there.
If they're still there. No, then maybe not. So then we'll thank. Let's just go again for the very next talk. Okay, so next week we switch back from non-commutative geometry to C-star algebras, and it will be Andrea Vaccaro from the University of Munster who will speak about tracially complete C-star algebras, tracial transfer and structure. So, see you again next week.